two regions. The two regions are indicated by the yellow. Those are the water bands, water vapor and ice bands. There's actually a third to the left that I don't show here at about 1.27 microns, shorter wavelengths to the left, that actually shows this as well. We got good fits. This was a unique fit, meaning we could not put other compounds in here and generate this same fit. So we were really excited. It was a pretty tight fit within the air bars for water vapor and ice. Now all those other bands and bumps there are of interest too, and we've been studying those. And I don't want to say too much beyond what I've already said on those bumps and wiggles, except the next slide shows that we can actually fit them all pretty well with a variety of different compounds. And that's when I said this goes beyond the water. It really does. There's a lot of stuff that came out of there. And you're going to hear about this a little bit more as we discuss this on the panel. But there was a lot of stuff that came up out of the floor of Cabeus, not just water that we saw. So the next slide then goes on to the next instrument. If we can have the next slide. This is the ultraviolet visible spectrometer. And what's really important to consider today as I come forward with these findings is we see evidence for the water in two instruments, two independent instruments looking at water two completely independent ways, and that's what really made us confident in our findings right now. This shows the radiance, or the brightness, measured by the ultraviolet visible spectrometer. Again, it's measuring the brightness as a function of color, and that's color or wavelength is shown across the bottom axis here. The red line shows the measurement. So it's a little bit brighter towards the right at red wavelengths. 660 nanometers are red wavelengths. What you see, though, that's important are some little spikes. Those little spikes are called emission lines. Emission lines are diagnostic of a variety of different compounds. So, and they result from when a compound, either a molecule or an atom, is in an excited state and relaxing out of that excited higher energy state. It releases some of the energy in the form of light and creates a sharp spike, an emission line. You can kind of think of it like a neon sign. A neon sign that's glowing red or green has a particular gas in it, gets excited, energized with electricity, and as those atoms in that neon bulb relax, they emit light of a particular color. That's what we're seeing here is species are emitting light at a particular color, and by understanding exactly what color that emission line is at, you understand what species is emitting it. So what we were interested in is some emission lines in the ultraviolet, and if we go to the next slide, we can talk about those emission lines. The emission line we were interested in comes from the hydroxyl molecule, OH. OH can be produced when water vapor, H2O, is broken up by sunlight. Ultraviolet sun rays will break up a water molecule into OH and H. And that OH is energized, it's excited, and as it relaxes from an energized state, it releases some light, an emission line, a series of emission lines even between 306 and about 310 nanometers in the ultraviolet. And that's the range we're looking at here. So what this figure shows is the ratio. What we've done is we've divided pre- and post-impact measurements to get rid of everything else we're not really interested in. We're just interested in stuff resulting from the impact, and plotted it as a function of color again here, or wavelength. And right in the middle where that blue color is, you see a spike that rises from earlier scans, which are down near the bottom, to later scans, which come up in ratio at time. And there's two things occurring here. The lines near the bottom are relatively flat in lower levels. Those are basically pre-impact scans. What those show is they're flat, not a lot going on there, and they're at a lower level. After the impact, we had an ejected cloud come up. It was scattering sunlight, reflecting sunlight, and that's why the levels in general come up higher and higher. What you can see then are spikes emerge in a variety of places, but the one we're interested in for today's discussion is right in that blue area. And you see a sharp spike come up right around 309 nanometers or so.